Good morning, class. Happy New Year, even though the month is almost ended. Today, we are going to continue what we were doing before, and we go into some example, a concrete example in general solid modeling. I'm going to spend some time on the example we have today. And if we can finish early, we finish early so that you can go and look at the assignments that I'm going to give you. Because like I told you before, in graphics and design, it is only what you have done that you know. Somebody told you something, you don't know it until you actually execute it. You don't know it. So we're going to look at some general issues in solid modeling. We're going to look at issues of coordinate system, issues of, but let me just go through the what I prepared. Uh, we will look at some aspects of solid making by revolving, lofting, and sweeping. We just look at some simple issues in those things. And then I want to discuss this thing in the context of either assignment or a large project that will be the culmination of this course. And the topic we will start with is placements, attachments, global coordinate systems, local coordinate referencing. So we will look at placements, attachments, global coordinate systems, local coordinate systems, and referencing things through either of them. And you will see why very often you prefer to use the local coordinate system rather than the global coordinate system. And then from my experience, I've been busy over the Christmas with free card drafting. I gained some experience there. I found out that it can really, really, really be discouraging when you try to follow the rules and you find that the thing is not working. And there are certain reasons why that happens. So we will look at some of those things so that you can have a better experience using free card. And then there are some things that are not provided for in free card, and you have to interact programmatically with it. Once you are coming to free card with your ability to code, the game changes. So it is no longer a simple idea that one software is better than another. If you can program in the software, there is scarcely anything you want to do that you cannot do. So we will look at some program intervention, just take you through some basic codes, and then you will see how to write your own program by it as your Python is getting stronger. And like I said, free card is one of the best ways to teach Python. You learn more about Python if you try to code Python in free card. And I will keep giving you examples of where that is really very advantageous. And lastly, you are going to have at least 3 assignments in this lecture. They are each of is simple, and it is good for you to pay attention to the kind of assignments I give you, because in the exam, you are going to have things that are similar to that in the final exam. So if many people think that drawing cannot be tested in an exam, it can be tested in an exam. What will happen is that we will not start from scratch. I give you something that is half done, and I tell you to finish it, knowing that you can finish it in 30 minutes. And that's a full question. Because if you can finish in 30 minutes, go to another one, finish it in 30 minutes. So you can be told to do things. So notice that the simple assignments I'm giving you are a foretaste of the kind of things you can be given in an exam. So if you don't pay attention and you just copy what somebody else has done, you will find yourself passed down in the red hand. You will be caught in the exam and you will not really have anywhere to go. I receive letters from students long after the class has finished. Students go as far as talking to other lecturers that they think know me to plead their case. The only thing is that students don't go to my mother these days to go and complain because my mother is dead. So they will have to die first to go out to meet my mother before they can. People do all sorts of things. You don't need to do any of those things. Just pay attention to simple things. There is no reason why you cannot get an A in my course. My courses are very straightforward and easy. You can get A if you do your work, and you can fail if you don't do your work. And once you have failed my course, I rarely ever change my mind because I am very slow to reach a decision. So once that decision is reached, I don't think anything else will happen other than you're taking the course again. So if you want to take this course once and for all, please pay attention to the simple assignments you are given. It is not just for the marks you score during the term, but for the implications for your exam. Even if you get 30 over 30 in the continuous assessment, you can get 0 over 60 in the final exam because there I can bring back to you the things I've given you in the assignment. Even if you got it in the assignment, once you fail it in the exam, the conclusion I draw is that during the term, you didn't do the work, you copied somebody, and I've caught you. So you can't tell me, oh, somebody got 27 over 30 in the continuous assessment, and he still had an F. So he was so sure that that's not possible, and he was drawing my attention to that. I just laugh. If you got 27 over 30, you should be able to get an A. If you are trying to now just pass, I know that you copied during the term. Anyway, I don't want to belabor that issue. You are adults, so you know what to do. So assignments are project based on this course and this class and next classes will be around a centrifugal pump. I find that to be a very good engineering artifact to design. And for people who have graduated, we have done the design, we have done the optimization, we have done the computation, and we have done a lot of things with that particular equipment using the theories of fluid mechanics, heat transfer, and so many other things. I think it's a good thing for you to be able to get a complete and actionable graphics at 200 level. The full graphical sketch that is prepared for simulation software. And then you will now design by analysis, computation, and optimization. And you'd be able to get the specifications for a determined service condition and look at possible improvements. And then for you to get into this, please take the trouble, read everything you can find, simple things on centrifugal pumps and the turbines. Just read about them. And then you'll be able to see maybe sometimes even some of the drawings, you'll be able to see some drawings from other sources that you can use to improve your own drawings. So those are things that are possible. The courses that are involved in the things we are doing is very wide. The courses, a very wide selection of courses from strength of materials to thermodynamics to heat transfer to fluid mechanics, graphics and design, and the mathematics. All these things play together. That is why the courses all those courses are design courses. And many people don't know that. They think it's only when you call a course design. The only reason why you are doing strength of materials is to be able to design structures with it. And that's the same reason you are doing thermodynamics and all those other things. In systems engineering, we do not take all those courses. We have continuum mechanics, which is the unification of all those courses as a single course. The only thing is that over the years, we have it only for 1 or 2 sessions, 1 or 2 terms, and it becomes optional in the final year. That is why you do not have enough of it. If you have 3 courses of it, you would have covered the scope for most of these things, and you'll be able to simulate in your final year for your project. I don't know what the department will decide, but we will need to make the courses on continuum mechanics compulsory. But right now, as far as I'm aware, it's only compulsory at the first level. But at that first level, all that you do is basic mathematics. You have not really gone to the meat of it. The meat of it starts from 400 level and ends at 500 level. But don't worry about that yet, because all we are doing now is how do we get the graphical entities that we're going to use for the simulation in continuum mechanics. So that one you can do now. I just want you to know that our drawing here, we are not just a hobbyist trying to do a 3D printing. We are training you to be engineers, and we are using the graphics here to be the input for your engineering design courses. That is the thing. That's why our approach is slightly different. Not that you can't learn from people who are all over the internet saying things, but I'm just saying that there is a limit to what they can teach you. So we go into the issue of coordinate systems. You can put graphical object in scope in a free CAD model by doing two things. The graphical object you have, maybe is a primitive like a cylinder or a cube or cuboid. You decide, since the thing is big, you decide an attachment point. It is that attachment point you place in the global coordinate systems. When you do that, that is a placement. So that if there are other things, for instance, if you are doing an assembly and you have three objects, you know precisely where those objects are located. So the object in question can be a sketch, and that sketch might birth a solid body. You might be doing a sketch so that you can use it to generate a solid body. It can be an imported graphical object. Maybe somebody did a 3D photography and it is bringing it in a particular format, and you are going to use that in your drawing. That could be the origin of the graphical object. You might use it for modification, or it can be an object that you created yourself in 3D, either directly or from a two-dimensional sketch. There are largely two strategies of coordinate system usage. One is the global coordinate system, and the other one is the local coordinate system. The global coordinate systems. The CGS, although it's not CGS, that is GCS. There's a mistake there. Let me correct that. Global coordinate systems, that is GCS. The global coordinate system is the default, and it's a fixed coordinate system for the document. That's where you begin most things. For example, if you just create a document, create a body, and you say, I want a sketch, that your sketch is fixed at the origin of the global coordinate system. And that origin is known. That's why when you are taking your sketch, when you are taking your dimensions, the origin is a known point. So you can refer everything to the origin. And the orientation of that original coordinate system, the X, Y, and Z axis, are also given. And it is customary to paint the X coordinate in red, the Y coordinate in green, and the Z coordinate in blue, so that when you cannot even read them, whatever is red, so it's RGB, that is the code. So red first, green second, and blue is a third coordinate system. So you remember this with the RGB sequence. All objects created without transformation are initially referencing this system. It is the reference for everything in your drawing, is the default reference for everything in your drawing. And then we now talk about the local coordinate system. Every object has its own coordinate system. Its reference to the global coordinate system is its placement. So you have the placement, and then from that attachment point, you can create a local coordinate system. The origin of this is the position of the local coordinate system in the global coordinate system or in the next higher level of reference. It is possible for a reference to refer to another reference to refer to another reference. But most of the time in this course, we are going to have our local coordinate system referring to the global coordinate system. So we have, most of the time, we are not going to have an intermediate level. So you may also define a rotation with respect to your global coordinate system. I keep writing it as CGS. I don't know why. The local coordinate system also has its own X, Y, and Z coordinates with its origin located at the position in CGS. The placement of an object encodes the LCS origin relative to the parent via the translational, that is position, and the translation and the position, or the translation, which is position, and the rotation, which gives you the orientation of what you are doing. You can define a rotation by selecting an axis and a rotation angle along it. That is one way. That is a very graphical way to define an axis. Just to define a rotation, just select an axis and say rotate this thing uh, 30 or 50 degrees. That gives you the orientation based on that axis. By the way, that's not the only way you can do it. You can define a rotation tensor, and that will be equivalent to this one. But that is a little bit more mathematical and not immediately obvious that you have a rotation. You need to know a reasonable amount of math for you to see a tensor and know that when we operate that tensor on anything, it does a rotation on the thing. Now we get to placements and attachments. As we said before, placement is locating objects with respect to the absolute global coordinates. It is absolute by default relative to the parent coordinate system, usually global, unless part of a compound or assembly. It can be set manually by editing the placement property in the property panel. For any setup you have, there's a property panel, and you can locate you can set the placement of anything by giving it a translation from the origin and a rotation where it has reached the place. That is how you do it. Attachment links an object to a reference object to which it is attached. And attaching something to a reference object is like gluing it to the object, and the object can be a face, an edge, or a vertex, or a datum plane. A vertex is a graphical point that can be displayed. I didn't say a vertex is a point. I say it's a graphical point. There are points that are graphical, there are points that are non-graphical. If you just talk about the coordinate system 0, 3, 5, yes, there can be a coordinate system 0, 3, 5. We can imagine in our mind that you have a coordinate system and you have an origin, and you move 0 in the x direction, you move 3 in the y direction, and you move 5 in the z direction. And the point, the location you have is a point, but it's not a graphical point. It becomes a graphical point when you use the graphic API to actually create a visual representation of that thing that can be seen in your graphics. When you do that, you are no longer just talking about a point, you are talking about a vertex. When we talk about a vertex, we mean a point that is not just graphical, but can actually be placed visually in your drawing. That's same thing with an edge. An edge is one or two more vertices in a graphical line. That line can be a straight line, can be a curved line. So that is it. And then a face is formed by a number of connected closed edges. So a face can be flat face, it can be a curved face. A face can be flat face, can be a curved face. But if you are going to do a sketch on a face, that face must be flat. So let us say you have a cylinder. There are two flat faces on a normal cylinder. You can use either of the two faces as attachments for a sketch. And if you do that, if at a later time the height of the cylinder changes, the attachment to that face will remain unchanged. All the references to the local coordinate system there will remain unchanged. So that is why when you want something to be immutable, you use local coordinate references upon an attachment. So you can move the attachment, but everything moves with it. And that is really, really powerful. And that is one of the one of the core principles of drawing, what we call parametric drawing. Parametric drawing. So that's why things can move and can change, and without making fundamental changes to the way your drawing itself is organized. And that's a very powerful tool. So we will just take you through some of the theory in using this thing. Many of the references you have on the YouTube don't go into the details. They just use these things, and you'll be thinking that it's a magic to know it. There are theories on these things which you can read from the manuals of FreeCAD or all the other drawing tools. Now we get to what is called datum entities. While faces, edges, and vertices belong to actual geometrical objects, datum entities are artifices created for the attachment reference. They are artificial, but they are things that you can see. You can see the datum references, even though they do not represent any physical object, but they are geometrical artifices. That is, an artifice is something that is created artificially for a purpose. It is not a real thing, it's an artificial creation. So they are artifices created for the attachment reference. So you can have a datum point, a datum line, or a datum plane. Usually a datum point is a point, a datum line is a straight line, and a datum plane is a flat face, it's a flat plane. And a datum line only has a direction. It doesn't have beginning and end points. Even if it shows you a beginning and end point, it's not real. It is just the axis. So in fact, it's more appropriate to call it a datum axis. And you can also have a datum plane. A datum plane is infinite. It goes in infinite directions all around. A datum point is a point reference with known coordinates. Forming a straight line with such a point can create a datum line. So you take forming a straight line with such a point, but you cannot form it with single point because it will be undefined. You need two. But it is not, even if you form with 2 points, the datum line is not limited to those 2 points because it is an infinite line. It's just that direction that it is representing. A datum plane can be created from 3 points. Those points could be datum points, they could be ordinary points, or you can create from a point and a line. So if you have a point and a line, you want to create a datum plane, it will take that point and it will create a datum plane that is perpendicular to the datum plane at that point through that line that you know. That line becomes the perpendicular, and usually it becomes the z-axis of that. So the remaining things to do is to now find xy coordinates that make that a right-handed system in your vector analysis that you know. So that's just all that there is to it. You can create, we will do some examples in this into this class. Note that datum lines can be created from real graphical points, just as datum planes can come from graphical points. So you don't necessarily need to have a datum point to create a datum plane. You can create them from ordinary points, and they will still be valid datum planes. Creating datum entities. Here I said begin with a polyline. We're going to do a demonstration now. You begin with a polyline. Select any of its edges straight of any of its edges, straight or curved. All is what I wanted to write there. And you can attach a datum plane, but the behavior may be surprising at first. I will show you this behavior so that when you get it, you will not be embarrassed and be wondering what's going on. Recall that you need 3 points or a line and a point to create a datum plane. And then we'll see how it plays out. Instead of the coordinate construction planes, datum planes or planes attached to flat faces can be used for sketches. So we're going to take some time out now, and I will fire up FreeCAD and do a fresh drawing, do a polyline that you can do. Hopefully everybody can do that now. And then on that polyline, I'm going to create 3 datum planes. And I will do some sketch and use that sketch for something for you to see how it is done. What I'm going to do is so easy that everybody should understand it from the class without even reading anything. It's so easy, but you can save it, you can do it, save it, and then look at it later on. It's just so dead easy that I didn't even send you this. I don't think I sent you this file because I'm not even going to use my own file. I'm going to start it from scratch here because it is really, really an easy thing to do. So let us go to our, so if you're at home and or if you have your computer with you, you too can fire up your FreeCAD and we will do the same thing together. So I'm running FreeCAD now. If you find that some of the things I'm doing are not easy for you to replicate in your own version, Notice that I'm using the latest version of FreeCAD. So, so you can download that if you want to. Mm. Screen sharing. So it's version 1.1 release candidate 2 I'm using right now. I wanted to keep to version 1.0, but sometimes there are things that I want to do that are not yet done there. And when I go to the newer versions, they're already there. And I'm not just patient to wait because the time of this class is going. And in the next 4 or 5 weeks, I'm sure we should be through with the lectures. So if you don't have it, you can download version 1.1 point release candidate 2. But if your version 1.0 is working and you are comfortable with it, just stay with it. It's taking long for my FreeCAD to load. But if you have your computer with you, follow the instruction I give you. Just take a polyline, any polyline. And then we are going to mark the polyline and then create datum lines, datum planes, and do something with those datum lines and planes. So what we are going to do, as I said, okay, I can begin by starting on a new document. And with a new document, I can create a body. To create a body. Okay, so what I want to do now is to create a drawing on the XY coordinate plane. If I create a drawing, I want to create a sketch on the XY coordinate plane. And oh, this is slow, and not responsive at all. Next time I will use my bigger desktop, which is much faster than this laptop I'm using here. Okay, so we take the XY coordinate plane here. It looks a little bit different from version 1.0. So we choose the XY coordinate plane as the plane to draw on. So I have my sketch XY plane. You remember the X-axis is the red axis and the Y-axis is the green axis. So let us just take a polyline and I start from a point here. And first of all, draw a line and then press M3 times and let that be a curve and do another line and press M3 times and do a curve and then end with a line. And if that is okay. So we have a sketch made up of these edges, a straight line, an arc, a straight line, an arc, and a straight line. So what we want to do now is that I will try and do a datum plane on this first line, and I will do a datum plane on the curved line. So to do that, I first of all close this sketch. You can go ahead and do some dimensioning, but that will take our time. So I can do that, but it will take the time, and I don't want to take time for that here. So this is the line we've just drawn. Now, if I choose this edge here and right click on it, and I can, when I right click, let me see whether even that right clicking gives me the ability to do the datum planes directly. Or I can go here and I ask for a datum plane. So I go to the icon there and I select a datum plane. So with the datum plane, you can see that the datum plane is on the same plane as the sketch. I don't want that. I want that datum plane to cross. I want that datum plane to cross the object itself. I want a datum plane here. Okay, so when I choose that, you can see now the datum plane is now at the beginning of the line. What can you see? You can see that the datum plane in this case is actually perpendicular to the line. So that means that if you have supplied FreeCAD with a line and a point, it is going to create a datum plane for you, and that datum plane is going to have the line you have chosen as a perpendicular to the plane, and the local coordinate system of that datum plane will begin at the line. You can find that to be true by now request for a local coordinate system. If you say that's okay, it will say that's okay, and we go back again to the same icon and we ask for a coordinate system. If I choose the datum plane and I request for a coordinate system, see what will happen. You will see that if you look carefully, you will see that there's a red axis coming towards me here. I don't know whether my screen will be clear enough. There's a green axis going up, and you know that the green axis is y-axis, and there's a z-axis going backwards. That is how, so you can see that there's a local coordinate system from that datum plane. So anything you do with that datum plane, that will be the local coordinate system that will be referencing it. And we can take the datum plane. Let us say if I say it's okay, and if I choose this datum plane now, and I can go to the attachment editor of it. For instance, I can see, first of all, it tells me there's a placement. Let us see the position of the placement. It says it's at minus 47 on the x-axis, minus 36.71 on the y-axis, and 00 on the z-axis. So because that origin is at the xy plane, it has a z component of 0. So what the things you are doing, FreeCAD is keeping track of all the coordinates. So this is the placement of the datum plane with respect to the global coordinate system. But it has its own coordinate system. And whatever you do along it can be with respect to its own coordinates. Let me do something interesting with it. For instance, we can choose the attachment offset. We can come here and choose the attachment offset. We can look at the position. Suppose I choose the position and you can see that I'm moving the datum plane in the negative z-axis. And you can see that it is not following the curve. It is following that axis that was defined. If I make that 0 again, it goes back to the beginning. If I choose a positive x-axis, it goes backwards because that is the orientation of the system. So you can always check where your datum is facing. So if we're happy with that, we have finished discussing one datum plane. Okay. So we have that datum plane. We can come again. Suppose I choose the curved part and I request for a datum plane. Let's see what will happen. You can see that unlike before, it is not, even though I gave it a point and a line, because the line is not straight, it puts the datum plane on the plane containing the curve. I want you to go to the chat room and try and guess why this is so. Why does it choose a datum plane, the first one? Why does it place the first one perpendicular to the line and the second one capturing the plane of the path? I want you to go to the chat room and try and see whether you can There are two things we are going to do. One, we want to explain why the datum plane is the way it is. And secondly, if our goal is to place a datum plane that is perpendicular to the curve, what do we do? So I want you to go to the chat room and see whether you can answer any of those two questions, because I'm going to answer them shortly, but I just want to see whether you can make an attempt. So I'm going to see you in the chat room. Why is this one perpendicular? So those the datum plane can follow the path accordingly. It's not following the line path. It depends on the plane position. The question is, why is the datum plane on the curved section lying on the plane of the curve? Is there anything we can do to make it perpendicular to the curve? Okay, Oluwafemi says he can't find a line which it can form a tangent with. No, it's not looking for a line to form a tangent. It's looking for a line to form a normal. The datum plane depends on the plane position. An existing datum plane is already perpendicular to the line. No, Oluwatobiloba, but that's not the reason. Oluwafemi Akinkuehi, you are very close, very, very close. Can you try again, or can somebody else try? Why? And then the second question is, what can we do to make this datum plane perpendicular to the curve, at least to a point on the curve? What can we do? I want more answers. And is the class sleeping? Wake up. Is it that you didn't get my question? The question is typed. Why is the datum plane on the curved section lying on the plane of the curve? Is there anything we can do to make it perpendicular to the curve? Adjust the axis by 90. No. By changing the angle in the by changing the angle of the attachment of set to 90. No. Okay. When you know the correct answer to the first question, you will see that it will give you what to do. There's another plane perpendicular. No. Let me change the question. What do we need? I told you this just now. What do we need to form a datum plane? What are the things that are needed? What are the things? That's another question. What do we need to form a datum plane? You can look at the last two pages. Okay. I told you what we need to form a datum plane. You need 3 points. That is one way. What else can you use? If you don't have 3 points, what else can you have and form a datum plane? Yes, Emmanuel Olanyika, you are correct. We need 3 points. What else? A line and a point. Good. We need a line and a point. When you supply a curved line, there is a unique line, and that is the line perpendicular. That's the line perpendicular to the curve. That's the unique line. So you can take a point there. So the only option you have given it when the line is curved is the line perpendicular. So, so it is taking any point here, and the line perpendicular will give you a plane that is on the plane of the curve. But that's not what you want. So when that's not what you want, what do you then do? When that's not what you want, you can take that sketch and edit it. Let's see. Let's see the sketch. Let me go back again. Mm. This, I'm not saying the things I need to see here. So let's say okay here and see whether there is anything here. I can't see the drawing on the, okay, yes, this is the body. Okay, so let us take the sketch that we have done and do an editing of it. Say edit sketch. So remember, this is the sketch. What I'm going to do here is that I will draw a line. Let me draw a line from this, a straight line. Now, I want this line to be tangential to this curve. So I will take the line, I will take the line and the curve, and I'm going to use the tangent constraint. Where is the tangent constraint here? This is tangent constraint. So with that, okay, with that, I can have, so you can see this line and this curve are now tangent to each other at this point. So let us say that is, let us agree and accept that and close. So if we close that, what we have, we now have a line. At this point now, we have a line. So let me choose this point. I've chosen that point, and let me now talk about a datum. No. Hmm, let's delete that. Oh. So if I now choose this line, I can now, and I ask for a datum for that line. So you see, I can now, because at this point again, let me rotate it so that you can see. At this point now, because this line is tangential to this curve, we choose this point so we can see that this datum is now perpendicular to the curve at that point because it now has this tangent and the point. So if we want to take a datum that is perpendicular at a point to a curve, we must first of all supply the tangent at that point. We supply the tangent if we don't supply the tangent at that point, the only perpendicular it knows, sorry, the only perpendicular to the curve it knows is the one that is coming out of the plane. But now he can see something that is perpendicular. You can see a plane that is perpendicular to the tangent. So you can see how we create the two. And again, here again, if we say that is okay, if we're happy with that, we can go again and select this datum and choose our coordinate system there. We can choose our coordinate system, and if we put a coordinate system on it, you can see again it has this z-axis. Let us take a look at it. Let me rotate it. You can see if you look, if the colors are clear on your screen, it's clear to me here, but I hope you can see it clearly. You can see the x-axis here, which is the red. You can see the y-axis there, which is the green, and you can see the z-axis, which is negatively along the tangent that we chose before. So that is the coordinate system we have here. And if we want now, we have this curve. We can have, if we now want to do, we will now, if we are now interested in doing sketches, we can now come to this one. I can come to this datum, select this datum. If I now say I want a sketch, if I want a sketch, that sketch is attached to the datum. So I can do something like maybe do two, let us say I do two circles, one circle there. Let us make it easy. I do a circle there. And then I say, okay, or let me just give it a dimension. Let's see the radial dimension of that circle, radius dimension, that circle. Let us make it 10 units. So that's fully defined, close. So you can see that there is something on that line. Let us do something else on the second line. And suppose I now say I want a sketch. I want a sketch on that datum. Let's see if on that datum I want a center rectangle. I want a center rectangle of side 15. Or since the radius there is 10, let us see, make it size 25. 25. And to make things easy for me, suppose I do some filleting at the end. I want to fillet this, fillet this, fillet this, and fillet this. Suppose I make that one, let's do a radius dimension there. Make that 5 units. And I create an equality constraint. I can create an equality constraint. First of all, choose this and this and this and this, and choose equality constraint. So everything is equal. So I can close. Oh, unfortunately for me, that's not where I wanted it, but let us leave it there like that. So suppose I take the second the second one here, and I want to do a sketch. I do a sketch, maybe one sketch at the center, and the diameter is 30. Another sketch, which is also an annular radius. I do another sketch here. and let the diameter be 40. Okay, so let's see whether that is okay. Close. So if you can look now, you can see that I have two sketches. And each of these two sketches, each is perpendicular to this. And suppose I want to do a pipe. Let's say, let me do a pipe, an additive pipe, and I want that additive pipe to begin at sketch 01. So additive pipe. So I choose that additive pipe. And the additive pipe is, oh, no, 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 that is, yes, so the profile is this annulus here is the profile. And then it's looking for the object to sweep along. So I can choose this original sketch as the object to sweep along. Uh, no, that is not good. So let me just choose the edges of the object to sweep along. I can add edges. I can add this edge and this edge. Or maybe I should start from here. Take this edge, remove edge. So I can choose this edge here. And choose this edge. Choose this edge. So I can choose edges. Then I can also this is, I'm not choosing my edges correctly, but I want to leave this one now. So what we have just done here is that we can choose things to sweep along. We can now make this thing to form a sweep along this. It's not working right now. There is something let me just cancel that. And I think we should be able to get this done in the class. So let's start again. Uh, so I want to do this one. So the sketch one is valid. Path to sweep along, add edge. Edge one, then edge. Edge two, and then add edge. And then add edge, and then add edge. Okay, so I've added those edges, and I can now go and choose which type of transformation I want. Is it constant transformation or multi-section? If it is multi-section, I can choose for the multi-section, I can choose this other one to add section. I can add this section to it. And if it's okay, A fatal error has occurred. So because I have chosen this, I'm able to choose an edge to do my sweep. If I'm okay with that for now, it's not agreeing to solve it. There is something a little bit more complicated here. I don't want to spend time on this. I will do this when you're on break, and I will show you when you come back for break. So let us take a break of 20 minutes now. I will do this before you come back, and I will show you on your return from break. So you can take your break. When you went on break, I saw what was wrong with the drawing. Let us make it simple. First of all, on the first datum plane, let us just edit the first datum plane. Imagine we just have a simple circle on that first one. And on the second datum plane, let us close that. On the second datum plane, if we take the second datum plane, which is sketch 3, let us edit that. Let us first, to start with, let us say we had another circle. Let us, on that second datum plane, let us clear what we have there now. Let's edit, delete, delete, delete. Delete, delete. Instead, let's just have another circle on that second datum plane. So take a center circle and put it on the second datum plane. And let's us say that the diameter is 25 or 20, or so take the radius and the diameter 25. Okay. Okay, so if we did that, the pipe is like this. But suppose we don't want the pipe to be uniformly round. We want it to be a square after some time. So we can go again and edit that. If we edit that, and instead of a circle now, we do a center rectangle. We do a center rectangle. Let us make each side 22. Enter. And say, okay, close. If we look at that, see what we have. So you can see how warped and distorted what we have here is. The question is, how do we correct this? There are two things we can do. We can round the edges of the square as we did before. We can round its edges, edit that sketch again, and round its edges. If we want to round the edges, let's see whether that will help. I can take the edges, and I can take this and this and this and this and this. Let me see whether I can do my filleting all at once. If I do fillet, oh, it didn't work. So let me do them pairwise. I'm so much in a hurry. Pairwise. But I can put my equality constraints together, so I can choose all of them. And then make all of them equal. And then select one of them and give a radius to one of them. let it be 6. Okay, that's okay. Again, when you look at it, it is better, but it is still not very good. Now, suppose I do another thing. Right now, this is a this is a multi-sectional pipe. I can do a third section. I have one section, second section. I can have a third section, and let us say I make this third section the same thing as what I had before. But before I do that, I have to go and edit the original sketch. I have to go and edit this original sketch and say edit sketch. In this sketch now, I want to create another datum plane there. So if I create a datum plane, where do I get my datum plane object now? There's a sketch. Oh no. So let me close the sketch first. I have to close the sketch and let us hide the additive pipe for now. So I'm interested in this edge here, and I want to create a datum plane. So yes, this is the datum plane option, datum plane. Okay, so let us see. Okay, so that's the datum plane on the last section. So what I want to do now is to do a sketch on that. So if I choose that datum plane, okay, and I choose the datum plane and I want to do a sketch on it. So the sketch I want to do on it is like before, a center rectangle. And that's, let us say that rectangle is 22, 22, 22. Okay, then I'm going to do some filleting again as before. Undo. Let me try again. Sketch. Center rectangle. 22. Okay, I want to do some filleting at the edges. So fillet. Again, as before, I want equality constraint, so I want to choose every fillet there. I want them to be equal. And I choose one of them. Use this dimension, make it 6. And then say close. So what I have now, I now want to edit that additive pipe. I want to edit my additive pipe, edit pipe. Now, what I want to do is that I want to add a section to it. And the section I want to add is the new plane I have created. I lost that again. Let's see whether I can see the datum plane. The sketch on it. Is there a sketch on it? So this is taking too much time. So let me just do the sketch without filleting. 42, 42. Close. Okay. Okay, I didn't lose that. So what I want to do now is to edit the pipe. Edit pipe. Edit pipe. So what I want to do is to add another section. I want to add another section and let that section be sketch 4 and say okay. Okay, so let us see what we have now. You can see that the addition of another section straightens and makes this one, solves all the problems that we had before. So that's just one way. So you can see that when you are doing an additive pipe, especially if what you are doing is not exactly the same all along the length, you are able to check that by making more sketches, and that one you can use a datum plane to your advantage there. So let us go back because our time is really gone, and we have not really reached what I want us to spend the most of the time today on. So let's go back to the stuff we are doing before. So we have seen here that we can create datum entities. We have seen how we can create a datum line, and you can see that a line is just a direction. We can create datum points when we need to, and the usefulness of that datum point is that we can use them as the nodes of a spline, and we can now use them as the input on splines. We can do that programmatically also, but let us just know that we can create datum entities, and the datum entities, you can use coordinate systems on them, and those coordinate systems do not change when you change things. Even when you move the datum, the datum carry them along unchanged. And that is very, very convenient often. So we can attach to a datum, and when you add anything you adapt to a datum, it's like it is glued to the datum. So that point on all references to its local coordinate system is fixed with respect to the datum, no matter what happens to the datum. So whether you rotate, you translate, you move the datum any way you like, everything moves with it. Because of that, because it's motion invariant, because of that, we want to refer our coordinates to the local coordinate systems that are attached. So instead of placement, most of the time you are going to be dealing with attachments. And most things have their attachment editors that can be used to change a lot of things on them. This is often a more convenient reference system than the datum and its local coordinate system. As the datum and the local coordinate system can easily be shown in your drawing without invoking their placements that are mutable depending on changes to your drawing. So this is a summary. In short, table here shows the features in a nutshell. So the feature, placement, or attachment. Purpose, set an object position and orientation. In the case of attachment, it links object to another object and you can create a local coordinate system there, which is immutable even with movement of that attached object, of that reference system. Dependency. The placement is independent, can be moved freely, but the attachment to a datum or to a space is dependent on the tangent. So once you move that tangent, it moves with once you move that target, it moves with the target. What about updates? Updates occur only when manually changed. In case of attachment, updates are automatic. When you change the attachment, everything is updated automatically to cope with the updating while maintaining the local coordinate system unchanged. Use case. You can use placement to move or rotate objects. But whereas attachment is for parametric constraints. You can see in the drawing we did last, you can see that in that drawing, what we did remained, we can edit the parametric pipe we created by just choosing another attachment and making it part of the stuff without changing any of the things we did before, and the drawing itself updates and it corrects the drawing and makes the drawing much closer to what we want at the end of the day. So those are the things, and you can see that attachments are used much more often than placements when the drawings become complicated. So we have had some experience in creating sketches. Our old sketches have originated from the coordinate planes X, Y, Y, Z, and ZX. I'm sure we have seen now that our coordinate planes can actually come from attached datum planes. So datum geometry releases us from such restrictions because our coordinate system are often associated with absolute referencing. Introducing a more robust referencing system that entities can be attached to as distinct from absolute placements. Such reference systems do not only create local coordinates, but are also immutable from changes as their references are preserved. We will now look at some practical examples. In creating solids, you find that part design is essentially solving geometrical relationship problems. When the problem cannot be solved, you just see, I'm sure some of you, if you have practiced, you will see that you just do some things that you expect them to work, and somehow FreeCAD tells you there's an error. There's an error because every geometry you are creating is solving a geometrical problem to make sure that all their tangents are correct, all their orientations are correct, and that thing is a possible geometrical shape. When it is not, it just cannot solve the problem, and it says that your drawing cannot be solved. So you may have to make sure that your gradients are gentle, your shape changes are small, and your lofting and sweeping through center lines are not supported directly in FreeCAD, but they can be obtained programmatically, as we shall show today and subsequently. New versions continue to advance. Today's lecture is done in version 1.1, release candidate 2, that you may download from the FreeCAD page if you need it. And the next example we're going to do here, we're going to just do a simple additive revolve. Just like we did a simple additive pipe. We do a simple additive revolve. And I have this, I don't know whether I have enough time to do a direct something here. Select one of, what you do, you just create a quadrilateral of 5 sides, select one of your sides and turn it to a datum line. Well, I think I should do this because it is quite instructive for you. I want you to all see that you can do it. It's not hard at all. So let us clear all here. Let's clear all and discard this. And then we start again with a new document and with a body here. And then we can start a sketch. As usual, let us start a sketch on the XY plane. We start a sketch on the XY plane. What I'm going to do, I just want to create a 5-sided figure. Any 5-sided figure that is convex will do. Convex so that there is nothing there that is closing upon itself, and that is necessary so that you do not have an unsolvable geometry. So this is a 5-sided figure. If I'm happy with that, I close. So the next thing I want to do is that I want to create a datum line along this edge. So if I want to create a datum line along this edge, I will choose the edge and look for the something for creating datums. So where is it now? I easily lose it. Okay, this is it. So I want a datum line now. So a datum line has been created there. You will see the dot, dot, dot as part of it, and it will extend beyond the edge to show you that it's not limited to that edge. If we're happy with that, we can click OK. So we can now go to a revolve here. If I say, if I click revolve, I want to revolve this sketch, and I click revolve, and it wants the angle. I want the angle to be no more than 120 degrees. The axis, I want the axis to be a reference to be selected, and the reference to be selected is the datum line. Okay, so that is it. The angle is given. Datum line, recompute, and if that is okay. Okay, he said the wire is not closed. Why? Why is wire not closed? Let me just do it again. Cancel. Cancel. Let's do again. But let me edit that sketch. Wasted unnecessary time in these things. Edit this sketch. Edit this sketch. And then this looks close to me. Close. Mhm. Mhm. So it's okay. So this is the revolution in the example that I have. So you can decide to make it a little bit more interesting. You can decide to edit that. You can decide to edit that sketch. And what do you do there? Edit sketch. If you edit that sketch, one thing you can do is that you can create an offset. So let us take the sketch here and I create an offset of it. Close that. And let us remove this revolution. Delete this one. Okay, so I want to create so I take this, 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 and this. So now I do a revolve there, and what I want is 120, and as angle, the axis, select reference, and the reference is this. That is the reference there. Datum line. What is the preview now? Again, like wire is not closed like before. So the origin, so we can do it in two steps. We can first of all do, and we can do this one that worked. No, this is taking a lot of time. So create a revolve there. The axis, select reference datum line, and this is 120. And click OK. But that wire is closed. 1, 2, 3, 4, 5. That is closed. And then mango. Axis is the datum line. Mango. Keeps insisting the wire is not closed. But I can't spend the time on this. I have it. I don't know whether I sent it to you. I sent you some drawings, but I have only 15 minutes left. So I just have to go on. Uh, the example I gave here, when I did it, this is the kind of result I had. Uh, when you when you choose one of the lines as the edge here, so you get this, you get something like this. It was just so simple that I didn't feel like giving you the drawing here. So you try this on your own. I can do it and send you a picture of it. This is how it is. And then you can now later on change the dimensions of the inner circle and see, smoothing it out, and you see it appear. So the next one, which is the additive pipe pair, which is similar to what I told you, you can see that here again, we have the datum reference at the beginning, another datum reference in the middle, and because the datum reference in the middle is not round, it gives something like this. I'm sure you know what to do here now. What you will do here is that you make it a third section. If you do a third section close to the edge here, it is going to be able to smoothen this one out for you. So I've already done that successfully in the one that I showed you earlier on. And then the next thing is a Boolean subtraction. Suppose you have something like this, which is open, and you want to take a section through it. What do you do? One way to do that is to create a solid cuboid and that hides one part of it and do a Boolean operation, like a Boolean subtraction or a Boolean cut on it. And then when you do that, you are going to have something like this, which gives you only one section of it. The last example, which is the one I want to spend the rest of the time on, and I'm going to give you things to go home and do, is this is just what we're going to work on for the next 2 weeks. That is after now, we are still going to have 1 or 2 more lectures on this. Now, what we have here is what we call a volute. A volute is a rounded object like this, but it is not, the round part is not a circle. Instead, it is a spiral. It starts with the smaller radius here, and as it is going out, it goes and increases to a bigger radius, and it ends there. But it also enters itself back. It goes round and enters itself. When you try to do a loft or a sweep that enters itself, FreeCAD goes mad, it goes crazy, and it does all sorts of funny things. So the solution to that is that you do it in 2 steps. You do it in such a way that it doesn't enter itself. And then you now come and do this other part. And in order to get this edge is very complicated. The edge that will fit inside this place and will make the thing enter exactly. That's what we will discuss in another lecture. But I will just give you this to play around. I'll give you the file here so that you can play around with it more than we can do in class. Because when we are doing things in class, we do not have enough time to go through all the issues. And we can just have a small error and that will take all our time. Here, the volute begins with a spline. The spline can be made up of points. You can take all the points along the spiral and allow the spline, the B spline, to create a point. It will create a spline with those points as nodes. That's one way to do it. You can do it manually. It takes time, unless you don't allow it to be smooth. If you allow it to be smooth and you are taking a lot of points there, it will take you a lot of time. So it is easier to write a program to do it. And the program to do it, there is a homework here, and that is the spline. And the next homework I'll give you the code. So I want you to study the code, use it. Once you have that macro, run it. But study that macro so that you can write something like that yourself, because it is just the parametric equations of what you have there is just a coding of the parametric equations of a spiral. That is all. And this is the spine of the spiral that you are going to get. You can see that this is it's looking like a circle. It's just that instead of closing, it offshoots. And after it has offshot itself, you now draw a straight line to some distance outside. This is how you begin the design of a turbine or a centrifugal pump. It has to be a spiral spine, and so many other things will happen. But this is the fundamental. This is where you start. And some some CAD programs come with spiral creation utilities. Something like Autodesk Inventor can do it. Fusion 360 does not do it. Fusion 360 sees it as something so trivial that you can easily write a code. And you will see it from the small code that we have written here to do this spiral, which I'm making available to you. The name of it is Spiral Spline Macro. So if you just put it there and run it, it will create this for you. And then if you now want to create, profiles, you can just create. If you are in part design, you can create. You can create datum planes and create as many profiles as you want, and then let these things just create a pipe through them for you. So this is the code. It's not long. It's a total of about 20 something or 32 lines. And most of it is the real essence of the code is about 6 or 7 lines. And if you type this in, or I think you have to type it in because I didn't give it to you in code. I just gave it to you as a picture. So you type this in and you can change it as you like, change the dimensions, and it's already with you. And then, so homework 2, I want you to check lines 26 to 27 in what I'm giving you. Find out why the for loop in lines 26 to 27. You find out what it does, why it works, despite the fact that the looping variable is absent from the body of the loop. I want you to rewrite the loop so that it uses a looping variable and get the same result. And check which is better of the two codes. For somebody who knows what he's doing, this is not going to take more than 10 to 20 minutes. Again, you think that one cannot ask a programming question in an exam. It can be asked. We will just not start from scratch. I can give you some partial code and tell you to do something with it. Or I can tell you to bring the code of a particular homework to the exam. Because one thing I want you to know in this class, all your codes, all your drawings should be saved, because I can refer to a particular homework or a particular drawing in the exam and say, beginning from what you did there, do this, this, and this. That's the way we test both the graphics and the programming in this course. So do not you can get help from your classmates, but do not just stay with that and say, "Oh, they have done it, we have submitted, and we can pass and forget about it." It is not over until you finish your exam, because every question that you have been asked can still be brought up during the exam. So that is it. And then I've given you, I give you this complete volute refined. It's already sent to you, so you have the file that does this very complicated work here. And then you now take that, given the volute turbine made by fusing the inlet and main turbine, you will see which one is the inlet and main turbine. I've already showed you before. This is the inlet. This one is the inlet. And this is the main turbine. And this one enters this to form this. This is what you form. You have the file here, so you can look at it from all angles. You can see that the center enters each other. Now, what we want now is to add an impeller to this. To add an impeller to this, we have to cut the central area completely open. We have to cut it completely open, and I want you to do that. Suppose you already have this, which is made up of this and this. And what you are supposed to do now is to cut the inside open. How do you do that? What you do is that you create a cylindrical primitive. In part, for instance, create a cylindrical primitive that cuts into this one. And then you do a subtraction of the two. If you do a subtraction of the two, we did last week, we did Boolean operations. If you do a subtraction, I will show you what the kind of thing you will get. If you do that, you should get something. I gave you the data. Beginning spine radius is 50, end spine radius is 60, with a straight section at the end. All this is already in the code that does the spine, which I've given you. So the beginning profile, this is what is not in the code. The beginning profile is 15, the end profile is 25. So what we are saying here is that not only is the radius of this thing increasing, the diameter of the pipe itself, you can see that it increases from here until it gets here. So it is not, so both the radius as well as the diameter, they are changing. And this is not a trivial graphical joke. This is how you do a real object like a turbine or a centrifugal pump. It must have a spine, it must have a spiral spine, and it must have a varying sectional, it has a varying section, and then it must be cut in the middle to put what is called an impeller. So I want you to read as much as you can about turbines and impellers. Read that. In the next lecture, we are going to carry this design to the next level. We are going to see how to add an impeller to it and then design an impeller. And then by the time we finish everything, you have a turbine that can be used for simulation and modeling and design. That is the thing that should be the result of this section. So this is how it will look when you cut it. This is how it will look. If you cut it, all the inside, this inside, when you get this inside place is cut open, and it is inside that you are going to weld the impeller into this inner space. So and then there is a pipe coming perpendicularly out of it. That is what sucks your water or gives pressure to your water. So one is the opposite of the other. The compressor does the opposite of what a turbine does. In the compressor, you put in energy and it moves a fluid. In the turbine, you put a moving fluid and it gives you energy out. But the design of the elements are essentially the same. They just work in the opposite direction. One takes a static fluid and sends it on a velocity. The other one takes the velocity of a moving fluid and it uses it to get the energy out, which can be used for generating electricity. But before you can do that, you must know how to do the volute, which the volute is a little bit tough. I want you to try as homework. Try whatever you can. Try whether you can do it once. I tried it and I could not do it except by doing it in parts. And I spent a lot of time on that. When I was using Fusion, I could do it in a single pass. But in FreeCAD, I couldn't do it in a single pass without errors. So I had to go through this artifice. See whether you can do it in a single pass using the methods that I've taught you in today's class. If you can't, don't worry, but you should be able to you should be able to cut the inner portion. What we mean is that internal portion must be cut open in a uniform way. And what you do is just let a cylinder interact with it, cut through it, and then do a Boolean operation to remove the part that has been interacted with. And when you do that, you should get something like this. And when you get something like that, here is a hollowed out volute. Use a Boolean operation between a cylinder primitive you created upon the volute to begin the creation of a turbine or a centrifugal pump. Know that the volute above is not a single object, it is a fusion of two entities. Attempt to create it as a single object as a challenge. Try, in case you can. Some of you may be more advanced in this FreeCAD than I know. So if you can do it, it will be instructive for the rest of the class to see how you did it. It is easier to do in Autodesk Fusion software, but when you use coding in Python, it becomes about the same. These are as I told you, the cylinder begins with, the volute begins with a radius of 50 and the spine radius of 60. The beginning profile is 15, the end profile is 25, and the wall thickness is 5. So if you create a Boolean cut, use a central cylinder of radius 55, height of 35 to cut an opening into the impeller inside the volute. So when you do that, this is the kind of thing you will get. I did not supply this to you because I will give you the solution of this next lecture. So between now and then, you try and do your subtraction and see what you get and submit it for your homework in next class. I think it's 12 o'clock. You can have a good day. Goodbye. Admin, I've done, so you can turn off the system if you want.
Okay, sir.
Okay, bye.